as we considered the city as a whole, but we also integrated individuals in it. We tried to model how behaviors from individuals can move and shape the city as a whole. The question is why to study this is because we need to understand the evolution of cities and also the obstacles that to this evolution of cities. The theories of cities, they have evolved through the years, and currently we are rethinking the way to design cities, as we think that the oversprawled city are over-consuming. So to study a city, we need to find an approach, and an obvious one should be the functionalist approach, but it's not really possible to use it because we can't clearly define what a city is or what the role is and why people live in cities. So as this question cannot be answered clearly, we have to pick another approach. So our proposition is to focus on the question of stability of urban forms, the emergence of forms and transitions from one to another one within the classical paradigm of complexity, as we consider the city as a whole, but with individuals having a lot of actions to do in it. So the starting point is the question of stability, because what we can observe is that in the world, even in different cultures, different countries, there are cities everywhere and they are quite stable. And even if there were transitions from certain forms to other one, these transitions were almost always quite smooth, and the cities are quite stable. And it's interesting because between different individuals, there does not seem to be an optimal strategy, and every individual should have his preferences. But we see that without having a collective strategy, we obtain a city that is well organized. So our approach is a morphogenesis approach. We try to describe how urban form emerges from complex processes involving the city as a whole, and the households, individuals, and public laws and policies. So to do that, we need a theory, and the one that we use is the theory of urban form that was introduced by Canadian geographer Gilles Richot. His theory was not practically formalized, but it says the following thing, that residential trajectories, over time, they shape an abstract form that constrains new trajectories. So we can see that in a city, for instance, if there were a lot of rich people settling here and investing in the city, they raise the value of the city, which means that people that do not have money, for instance, they cannot settle there. So they really shape this abstract urban form. So as I said before, this work is not practically formalized, so we cannot get properties from this. So at the city level, if we put ourselves in at the macro scale, Gilles Richot described the city according to two different axes. The first one being endoregulation and exoregulation of residential trajectories, meaning that people can or cannot choose where they live. And the other one is focus or diffusion of residential trajectories, meaning that trajectories, they either converge with each other or they diverge. And by crossing these two dimensions, he obtained the following matrix with focus and endoregulation giving gathering, exoregulation focus giving concentration, diffusion and endoregulation evasion, and diffusion and exoregulation dispersion. And he characterizes these four notions with concrete examples. So for our model, I think that it's important to talk a little bit about catastrophe theory, because we will use it. The idea is not to do a full course on it, but just to present the main aspects. So the thing is that we use this to model catastrophic changes in a system. So the idea is that we have a system, S, it can be in different states, and we have an external control space named omega, and S omega represents the system for the external parameter omega. Here I decided I showcase what the external space could look like, with each color representing one state in which the system can be. So for instance, we can think of a physical example like water that can be in different states, whether it be liquid, solid, or gas. And if we draw the diagram of pressure and temperature, we can see that there is at one point the triple point at which the water can be in 3 different states. So this point is a catastrophic point, because as we cross continuously in the external space, the system switches discontinuously from one state to another one. So if we have our city, as we defined before, with the 2 axes being regulation and focalization, in the framework of Thom's catastrophe theory, we can obtain this cusp model with certain forms that are stable and other ones that are not. So we can see that for some same parameters of focalization regulation, the system can be in 3 different states, meaning that this is an unstable one. The shape that is on the axiological space is a cusp, and inside that cusp, the parameters are linked to a city that is not stable. We can see that if we just walk on the surface, we can switch if we are in the regulations part of the surface. We can see that we can discontinuously switch to diffusion from focalization, and that is a catastrophe switch. So this model is good, but it's not what we wanted to do, because these 2 axes that were defined by Richard are more global notion and not local notion. So we have to define it for the individuals. There are collective properties rather than individual one. So to build this bridge between the individuals and the collective behavior, we need to first refine the axes that were presented by Richard, as the endoregulation, exoregulation becomes an universe of choice. So we have households that can decide where they want to settle, and if they have a lot of choice, then they will be on the right side, and if they don't have a lot of choice, they'll be on the left side. And focus diffusion becomes the axis of motivation of residential settlement. So on the y-axis, if a household is high, it means that is motivated to settle there, and if it's negative, it means that it is not motivated to settle there. And we can think that a household that is motivated to settle somewhere is more likely to drain with him other households that are similar to him. So in that axiological plane defined by these 2 axes, we model the individual behaviors via diffusion of ideas. So if there is one hotspot that appears at one corner, for instance, it will diffuse around him, as I mentioned before. So now we can present the model. So we have M is the space in which the variable representing the city is evolving. We have U, which is the axiological plane that we defined previously with the 2 axes that we have refined from Richard's initial work. And the stability is based on the dialectic between the position of the city in M and where the households are in M. So the barycenter, for instance. So there are positions that are stable, others that are not stable. But the thing is that they do not evolve in the same space. M is not equal U, so we need a way to compare them. So with the mathematical trick, we embed M in U, and we assume that the given geometry is an ellipsis. Actually, it's a closed boundary of the origin, but by deforming the axis, we can always obtain an ellipsis. And now the whole stability problem revolves around the equilibrium of the given ellipsis. So here I will just show an example. So on the upper images, we have the axiological plane, and the red dot is the barycenter of the households, and the green dot is the most stable urban form that is selected by the system, and this green dot is on the ellipsis that we defined before. And here we can see that as the individuals shift, as the barycenter shifts downward, the selected urban form will drastically switch from one to another one, as illustrated with the rotation of the ellipsis. So here, for that case, on the figure 1, we have little options for settlement, and they are middle in terms of favoring their residential choices. So we can think that it's something like a paternalist industrial city. And the selected urban form in the second case, where the preference for the settlement is quite low, is more like a sprawled city with the workers living in the periphery of the town. There's one thing that we are still working on, is the resilience of the geographical substrate, because this model is quite theoretical, and in practice, the urban form selected by the system will not automatically be the exact same one given by the catastrophe machine. So we need to install a coupling between the spatial temporal box of states and the theoretical space. So here what I showed is that in the physical space, which is the spatial temporal box, we can have a dynamic that push the city from one form to another one. Then we have to compute with the catastrophe machine the urban form, if it's stable or not, and if it's not stable, which one is selected. And depending on what is selected, we have to install a kind of retroaction on the actual physical space. So to conclude, we developed a formal model for the emergence of collective behavior from individual choices, and then it creates morphogenesis in the framework of Thom's catastrophe theory. The model is abstract, taking into account decision-making as diffusion of opinions among the individuals and households. And finally, it's something that we will probably work on, is the possibility to couple this axiological model with an economic model for housing prices. And thank you to everyone for listening to me.
Thank you also for an interesting presentation. Just a quick reminder for the audience that you can leave your questions in the chat, or just raise them at the end of the discussion. We will have a 20-minute session for Q&A. Moving forward, our next presentation is by Michele Tirico, Stefan Balev, Antoine, and Damien, Olivier. Entitled Morphogenesis of Street Networks, a reaction-diffusion system for self-organized cities. So if I could add the screen, and we can see the screen perfectly. So
hi.
The floor is yours.
Can you hear me?
Yeah, we can hear you, and we can see the
okay.
properly.
Do you see my screen? Yeah.
Thank you. That's great.
Okay. Okay, thanks. Hi to everyone. I'm Michele Tirico from University of Le Havre, Normandy, and I am book at I will the title of I will show some work that I do in last year during my PhD, and the title of this presentation is Morphogenesis of Street Networks, a reaction diffusion system for self-organizing. And I will present this work. I will introduce the topics. I will show the model. I will show also some results, and I will discuss some of them. And I will conclude and show some perspectives of this work. So the key aspect where we focus in this work is about cities that had been seen from a complexity theory point of view. So basically, we see that like a set of heterogeneous element that can eventually move over the space, but sure that they interact each other, are in relations, and those relationships are completely decentralized. And the second aspect that the cities are an important part of the cities is probably an underlined street networks, underlined spatial network that is typically is the street networks, and that can be represented through the graph theory, and the networks that you obtain is basically nodes are embedded in the space, and links represent a physical support of the system. And one aspect we focus on that is to study how this network evolved during the time can grow or for example, or can transform his part and can specialize its subparts in a word that come from Turing theory is the morphogenesis of a complex system. Before to try to understand how this network, those network evolved during the time, we had before focused on the main properties of those networks, and we can observe it compared to other complex networks that the degree distribution is very different in this case. In street network is typically picked around 3 in this case. And also, those networks are also, we can observe an high hierarchization of those networks. For example, there are some patterns that are more important than others. And also, in those patterns, those networks, it is easy to find a lot of path between the two different starting points. So that means the network is really yours. And finally, those networks are characterized that many characteristics can be observed locally. So we can observe subparts with different properties. In this example is the cities of Le Havre, for example. And how you can see a city in a very stylized manner. We suppose that it is we have different layers. Basically, we have an environment which contains physical properties of the space. Then we have urban fabrics that represent the physical element of the cities, like build-up. And connected with them, we have urban forms. Urban forms are some properties that are typically spatial embedded and concern, for example, social aspect, economical aspect, perceptual aspect, several of them. Clearly, these patterns are not static, they evolve during the time and constraint between them. And in this, so we can see forces between them that influence the evolution of the system. Clearly, the street network is an important part of them. And we also observe that those patterns and street networks are strongly related. So a set of cross-layer feedback can be observed between them. So we can consider the morphogenesis, we can study the morphogenesis of street networks, keeping in mind that we have several layers, which each of them have some properties and interact each other, and the cross-layer feedback impact those interactions. A second aspect that is very crucial in this work is the starting point of view of from complexity theories, and more precisely in the pattern formation in nature. We are inspired. There are several theories that try to explain how we observed in the skin of animals, for example. And one of them is the reaction-diffusion theory, where the key element in this theory is the idea of morphogens. Morphogens are a specific kind of element in a system that are form-producing. That means thanks of their concentration in the space and their arrangement, the system growth, evolve, transform in the time. And we can simulate the evolution of morphogens through basic mechanism, a mechanism of interaction. So we can simulate it with the reaction, chemical reaction, a mechanism of movement, that is the diffusion in chemical, and also a self-regulation of their production, represented without catalysis still in chemistry. So keeping in mind all those ideas, we proposed a multi-layer model to simulate the street network morphogenesis. Basically, it is composed by a first layer here is the reaction diffusion layer, where two kinds of morphogens behave, and in some circumstances they formed some patterns. When a pattern emerges, that means in a specific area, that means we have a gradient of concentration of over the space of those morphogens. That thanks to this characteristic, we can make a vector field that represent the evolution of those morphogens, and represent also the impact that it have to the unevolving spatial networks. When the network grows during the time, it feedback to its morphogenetic element, so it feedback to the morphogens in the reaction diffusion layer, and this mechanism it is allowed by a fourth spatial layer, that is a spatial environment that integrated those transformation, those impacts, and also, as we will see in the next, so all other properties and characteristics that can impact of an urban system, that can eventually impact the evolution of a spatial networks. So here I just show two basic simulations where all parameters in the first row and the second row is similar. We just change the parameters where we set the pattern formation. So in the first case is here we have all, and the second case we have mazes. And it is important to say that just change the pattern formation, we obtain different kind of networks. And as I said before, an important role have the feedback in general in a complex system, in this work, it was considered a cross-layered feedback between the reaction diffusion layer, so the morphogens, and the network. The network grow and feedback on to the morphogens. In this simulation, where we do not consider the feedback, is a test simulation. So we observe a quite symmetry of the growth of the network, and also we are not really correlated the network and the patterns. it changed a lot when we consider the feedback. In those three simulation, we make three different kind of feedback, and we observed and we just add the feedback a bit to the first cases, and we did not change other parameters, and we see that we different kind of patterns, mixed pattern, and also unexpected patterns. Moreover, those patterns are strongly related to the growth of the evolving network. And moreover, we observe now that the feedback also have a strong impact on the rate of growth of the network. Then we also consider another important aspect in general during the process of formation of string networks. That is that there are a lot of other environmental aspects that we must to consider in order to make a coherent and realistic simulation. So one of them is probably the orography of the environment. So we had considered that in integrating a second vector field in the model that represented the orography, the geographical orography of the environment, and through a few parameters we are able to simulate, for example, here a physical barrier with not allow the network to grow, and also a barrier that where is not a strong barrier. So, for example, that means simulated an hill. We just change the magnitude of the vectors. And the final example, we can simulate the case where we have some barrier that can be crossed in some times, like a river. Then we also applied this model in order to simulate the growth of a real context, because was important for us to understand if the model make networks that are still coherent with the starting point, and also see if you can make different scenarios. And in order to do that, we integrated several other parameters. We improved the capacity of this, improved the complexity of this model, integrated, of course, the orography, and also we integrated the build-up, density, the green area, and the political decision. How we do that? When you create our spatial environment, it is a regular grid, so of shell. At each shell, we can assign a set of characteristics, of properties of the reality. So in this situation, we set, for example, the build-up density. The build-up density will be in the second step correlated with the rate of growth of the network. And for example, we can reduce the probability to growth of the network in a specific area where the build-up density is very high. For example, the similar choice we can make with the green area or other area that the political when policymakers decided to improve the growth, to increase the growth or not, for example. And we make different simulation, and we, for example, here I presented obtained from the same initial configuration 3 different simulation obtained with 3 different patterns, and we also observe that the growth is different, the rate of growth is different, and also in this case we analyzed the between central, the spatial distribution of it, and we observed the different distribution. That means that we can obtain different scenarios from different initial configuration. And then we also measured for the between centrality of the statistical distribution of between centrality, also the statistical distribution of vertex degree, and more other indicator. That is some of them that we considered. The point is that compared to the starting network that we can see here is the dark, the black line here and dot line here. We observe that all obtained network, their properties are still close to the starting point. and there are also still really coherent with street networks, so the growth is coherent. And then we also observe that as we expected, the growth, the network to go toward a more organic and self-organized form. And we can observe that, just observe this distribution where we see many bifurcation, and so as consequence more than 3-degree node, and is here, for example. And with the Bettina centrales, we observe an increment of hierarchization. They go in this direction, the distribution, and that means that we have many more tree-like structures. So in order to conclude this work, I want to say that the starting point of this work is the complexity theory, and that is based on decentralized interaction, and also feedback. Feedback is very important in this work in order to control and understand the interaction. And actually, the feedbacks play a crucial role during these processes, because as we expected before to study this work, is that we cannot have you cannot consider the growth, the evolution of a street network just something that is inside, processes that are inside of the street networks. So we have to consider exogenous aspect for the street network, so the other environmental aspect of the street network, and we try to integrate that with the reaction diffusion layer, and those exchange that we have between the patterns and the street, so the different feedback allow to create an unexpected and sophisticated behavior of the model. To this model, it can find several applications on different scales, and also in different way to reply different problems. For example, investigate the historical evolution of street networks, and also we think that it can be helpful when urban planner want to try to simulate to apply some idea, and they try to simulate it and see what will be the results. And finally, all the network that you obtain are still coherent with the real network. I didn't show here, but we have make also other simulation where we compared a set of simulated network with department of French the street network. So we observed that they're very close. And finally, the perspective is that is considered the starting point, that is the notion of morphogenesis. This notion that is, I think, is also complementary with the work that it was present by Arthur and Olivier before me. That is, this starting point is a little bit different, because we focus with those elements that generated the system and improved the evolving of the system. Morphogens, as I said before, spatially embedded, are moving the space, and they are in continuous interaction. So we think that is a very behavior that very stylized, that it can represent several other real elements in urban cities. Like, for example, the population is very similar like that. And then other perspective is that better improve our understanding in this of this model, with a better evaluation of the model and the calibration of it. And clearly, we have also to improve we make some other experiment in a real context to simulate the growth of several other cities and try to compare them. So, thanks you a lot.
Thank you, Michael, for the presentation. It was quite interesting.
Thanks.
Questions that we will be addressing in the question and answer session after our last presentation. Michael, if I can ask you to mute your mic, I think, because I'm hearing some feedback on my side. So the next presentation will be by Hanae El Gouj, Bouman, Liubov, Tupikina,
Okay.
and Claire.
So I will reply at the end of the. Okay. Yeah.
So we have
okay. Thanks.
For clarification, we have a 20 minutes discussion session at the end of.
Okay. Thanks.
It should be after the next presentation. We will have questions for all presenters. So please feel free also to leave your questions in the chat if you need.
Okay.
If you can mute your mic so that because we're hearing some feedback, that would be great. So yeah, I'll repeat because of the echo sound. So our next presenter is Hanae El Gouj, Bouman, Liubov, Tupikina, and Claire Lagesse, entitled Road Network Characterization to Understand City Evolution. So if Hanae is here and she can.
Yes. Yeah, I'm here. Can you see my screen?
We can hear you and we can see the screen properly. The floor is yours. You have to.
Yeah, thank you. Hello, everyone. Thank you for being here today. So I'll be presenting our work on road network characterization to understand city evolution. I have been working on this work with Paul Bouman, Liubov, Tupikina, and Claire Lagesse. Our presentation will be structured as follows. First, presenting the research context around this work and why we focus on the road network to understand city evolution. Then presenting our approach to characterize those road networks based on Waze, which is a geographical object developed within this method. Then this approach will be applied on the city of Dijon in France. So just to give an example, and it's calculated on the historical road networks of the city from the 17th century to nowadays. Then we'll be present some results on structural changes computed on those networks. Finally, we'll discuss briefly modeling and the simulation of city evolution. This part is still work on progress within this work to finally conclude with our research perspectives. So why road networks? Cities and road networks are closely linked, and when we are trying to understand cities as complex systems, as it was already presented by other person within this session, we try to really simplify how we approach the city. So for us, road networks are really structural and structuring elements within the city. And one of the three morphological entities that form the city, we have road networks, land plots, and also buildings. But even after a disaster, as you can see on those two pictures after the tsunami in Japan, road networks remain somehow stable. So whereas buildings are destroyed, they can be rebuilt afterwards differently, or even when the plots of the city are merged or subdivided, this change all the time, but road networks are usually subject to little change. This also said that despite their resilience, they still grow and evolve over time. So our research suggests the initial hypothesis that the spatial light of road networks, if it remains stable over time, it can reveal the territory past organization and can give us insight into the morphogenesis of the city and how it's evolved. So we are adopting a morphological approach of city evolution, and by adopting the tools and method of graph theory and also complex system theory. So the morphological approach was developed by studying the spatial structure of the city via a graph representing the road network. And so road segments are represented by links or arcs of the graph and their intersection by nodes. So when studying city evolution based on road network, one of the biggest challenge is data availability, especially when we are considering a broad time frame of the evolution of the city. So in order to characterize those road networks through time, it was essential for us to acquire the digitized geometry of road segments from current road segments. For our case, it was from the Benichou, from the National Geographic Institute of in France. And then the geohistorical data was provided from historical maps. So these geometries should be matched from one map to another for the same territory in order to be able to trace their morphological evolution over time. So what we propose here is to digitize the historical road networks based on present day network to ensure this data matching. And we start by overlaying the Benichou current road network on each historical map. And as you can see on the picture on the left, and we can ascertain whether each segment of the current road network is present, absent, or should be modified on the historical map. So finally, road segments requiring adjustment are fixed and the missing ones are added. Missing ones meaning those that are not present on currently, but was present before. So from this historical maps, we were able to reconstruct historical road network. Here we are presenting just the case of Dijon. So we reconstructed all the historical networks. However, the spatial coverage of those historical maps representing urban areas is often small and does not necessarily embrace the total spatial coverage of each city and its evolution. So while characterizing those networks as they evolve over time, it is initially expected that the network properties might be influenced by the size of the sample of the network we are studying. As I said, as the spatial coverage varies with the coverage of each historical map from which we extracted the network. So this is why we apply the methodology of building ways. So roads are modeled as hypergraphs composed with nodes and ways, not arcs. So ways are constructed from the road network by combining consecutive road segments according to their minimum deviation angle and without respecting a threshold of 60 degrees at each intersection. So we have a continuous element on the network, and the road segment with the deviation angle exceeding 60 degrees remain separate units. Here we can see some network indicators. We have the degree centrality and closeness centrality calculated on arcs on the left and on ways on the right. So network indicators reveal this underlying structure of the city on both, but when calculated in ways, there is a very limited border effect, and the robustness of the network sample is really valuable for computing and characterizing those networks independently of the network sample we are studying, considering the variation of each historical map covered zone. And also ways allow us to have really a continuous element within the network, which is really reliable to the functioning of the city. To characterize those road networks, we are focusing on 3 indicators, simple indicators. So we are adopting a keep-it sample method to really characterize and understand the city evolution. And network indicators can particularly are particularly useful to assess the evolution mechanisms of the city. So first we have the degree indicator, which corresponds to the number of other ways a certain way or a reference way intersects, and it allows us to identify the main structures within the network. On the map on the right, we can see that the highest values represented here in red are the main structures of the city, and they correspond to basically the avenues, the boulevards, and departmental roads, or even national within the network. Then we have the orthogonality indicator, which characterizes a way according to its angle of connection with its direct neighborhood. And basically, this indicator highlights how each way is included in the network between 2 extreme cases. So highly meshed structures are going to have the highest level of orthogonality, I can cite the example of the Manhattan grid, and flexible connections such as tree-like slums are having like the lowest values of orthogonality. Then we have the spacing indicator, which defines the average distance between two connections by dividing the weight, the wavelength, so in meters, by its connectivity. And this indicator characterizes parts of the network concentrated in dense structures and those with wider spacing, such as the ring roads, for example. So after that, what we are trying to do is crossing those indicators. We have this first reading of the structure based on those indicators. Then to really understand how they are related, we are crossing those indicators and applying them on the historical road networks of Dijon to identify some patterns over time. So in this first figure, we can observe that ways with the high degree centrality and low orthogonality correlate with tree-like structures, whereas ways with high degree centrality and high orthogonality correlate with gridded structures. And this property can be also validated over time when we are computing those indicators on all the historical road networks. Then on this second figure, we are crossing the spacing indicator and the degree indicator, and we can see that high degree and low spacing highlights the city core, and it's still the same. So from the historical network from the 17th century until the recent one, we can see that it highlights the city core. The crossing of those indicators, so degree spacing or degree orthogonality, then orthogonality spacing, gives us insight for the reading of some patterns, and these patterns are stable over time. So it's really a methodology of reading those structure and how they evolve over time. And it highlights, for example, main exploring roads and also the main crossroads, which are the backbone of the city. And we can observe here that ways with high spacing and no orthogonality correlate with urban expansion, and ways with high orthogonality and low spacing correlate with a densification process of the network. Next, we consider here how different indicators vary as city grows, and we can visualize that this process by plotting trajectory evolution of the coefficient of variation of two indicators each time through time. We have here, I think, 8 or 10 time steps. So as cities are growing, we can see that there is a complex combination of plant graded structure and organic structure emerging. Here it's the case for the city of Dijon, which it can be confirmed by urban planners that it was the case for the evolution of the city, but we are trying to really have a generic method to read in the structure and apply this method on any other city and have the same reading elements. Finally, about modeling and simulation, about computing structural changes of the network. So here we have the difference of accessibility according to added edges and removed edges of the network. Here we can see between 1719 and 1883 the impact of the added edges on the accessibility of the overall network. And when we zoom in, we can see that basically it was a positive impact on the accessibility on the network. From 1883 and the 1944, it was just increasing in terms of accessibility within the city center. Then from 1944 to 2009, we can see how the evolution of the city impacted decreased the accessibility within the overall network. Expect this part, the north and east of the city core, the circle center, which was impacted positively, but mainly the overall area around the center decreased and was less served Then for modeling and dissemination of urban growth, we intended to combine the analysis we did on real data with simulated growth of the city using the model from Courta. And it was implemented by Marie-Sophie Graffito, who were master students working with us on the project. And then basically considering three geometrical features: the organic ratio, the meshness coefficient, and the topological distance. And the algorithm initially draw a potential center in the radius of the network. Then it chose the best new center using the potential function, connect this new center to the existing network. Then the network consists of n number of centers and stops at certain points. So the potential field that is considered in the potential function consider three main way of the development of city. Either it's radioconcentric or linear or multicentric. And then with the model, we can vary four simulation parameters. We have first the planning type, and it controls whether the city grows organic or centralized structure. Then the constructor factors control the number of roads added in each step. The organization factor determines the effort spent on finding new good location or expansion with the algorithm. And then the sprawling factor controls whether expansion focuses on inner development of the city, so densification process, or expansion outside current boundaries. And here we try to have a simulation from real data from Dijon in 1839, and we have the result from the simulation model and the real growth of the city. But from the simulated one, we didn't have enough time step. As I say, this is really still work on progress on the model. And here are some other examples from this model. So to conclude, in this research, we analyzed the evolution of the road network of Dijon through indicators based on ways to have this continuous element within the whole city using just three indicators. And they already can help us identify and highlight structures and patterns within the network. So what we are aiming to do is really comparing the trajectories through time of different cities. We have data on the Burgundy-Franche-Comté region in France, so we already have other cities. But it would be really interesting to implement this method on different cities all around the world and with different logic of evolution. Then identify the mechanism leading city evolution based also on network centrality. So it would be interesting to compare the trajectory through between centrality also or closeness centrality. Then carry on modeling road network morphogenesis and simulating their growth with the model, characterizing the simulated network with the same indicators, and then comparing the morphogenesis of real and simulated network. And the final objective is really to define prospective scenarios for urban development, considering different tuning parameters of the model, and also orienting different scenarios. For example, a city walkable without having the car, or really some utopic, for example, scenarios of the evolution of the city, or also, as it was mentioned from the previous presentation, it can be really helpful for urban planners to really test some scenarios of their urban project. Thank you for your attention, and if you have any question, we'll be here. Thank you.
Yeah, thank you, Hanae, for the presentation. Quite interesting. We have a set of questions. I think I will go through them in the order of where they were in the chat. So our first question comes from Olivier to Michael. He's asking whether you can explain again what are your morphogens X, Y, and Z, and what is the meaning of X producing Y, destroying Z, autocatalyzing, etc.
Yeah, let me share my screen. Maybe it's helpful. So basically, I didn't go too much in depth during this presentation about the reaction diffusion model. It is completely based on the Turing theory. So the reaction and the diffusion over the space, and more precisely in this model, I selected a specific model that is based on Turing model that is called the Gray-Scott model, that is still a reaction diffusion model. And basically, this model is composed by three parts. The first one here we have when we represent the dynamics through a system of differential equation, we can simulate the concentration of two morphogens A and B, and we can consider the diffusion in the space through a Laplacian here, with two different rate of diffusion in the first step. In the second step, in the second part, here we have the reaction and the autocatalysis of the morphogens A and B, and then we have a third part that is called the external part, that is you can see that we bring some morphogens and we trash some other morphogens, and we model that with two other parameters that is called the feed and kill EC. So combine this, that is the general idea, but I implemented this idea in this general idea in a continuous media. I implement that in a discrete media, and I implemented a cellular automated layer where we have a grid, and into each shell we have the concentration of the two morphogens A and B. So I hope that that is quite clear. And also I see that the second question, we actually as the diffusion is considered in the space. Yeah.
Thank you, Michele, but it doesn't answer my question on what is A and what is B in your system. What the physical meaning or geographical meaning of this quantity? If you can comment a little bit on how your quantities.
Yeah, the starting point is to make a model that is very, very, very general, that can integrate the different aspect. The idea is that in a real urban system, there are some elements that can have those behavior. One of them is clearly the population. Population in a very, very, very stylized manner, we can consider that they move in the space, that they interact each other, and also the concentration, the number of human evolved during the time. So, and it depends of this kind of interaction. So, in a chemical, from a chemical point of view, that is an autocatalysis. And you can simulate it with the autocatalysis, with the reaction and the diffusion. That is the idea. And also the idea of the Turing model is that you have two kind of morphogens. So one of them, it may be the population, and the second one maybe can be an economical actor. So we can see, for example, when we see in some specific area where we have more an improvement or an increment of activity of for example, industrial or also selling or different economical activities are correlated with the population. So the idea is that with this model we can consider two different actors that have an impact on the street network, that interact each other, and that contribute to the growth of the network. That is the idea, in a very stylized manner.
Okay, thank you for the clarification. I think, yeah, we'll move to the next question.
Thanks.
The next question is to Bowen Zhang, but it was a recorded session. So if Bowen Zhang is here, yeah. Okay.
Yeah.
So the question is from Olivier as well. How does your method compare to the intramax procedure by Massey and Brown in 1975, if you're familiar with that?
Okay. Firstly, thanks for his question, and I think it's a very good question. And I didn't know, I haven't know this kind of the research very well, but based on my understanding, I think during that time, the 1970 years, the intramax procedure is trying to just simply try to maximize the intracity or the minimize the intracity. But nowadays we have the urban mobility data, so we can trying to fit the like the specific trip distribution, not only the just the trying to find a trip like the maximize the intercity or something like that. I think that is the main difference.
Okay, I think we move to the next question. Thank you for the clarification. I think Zhang Ye had a question, but if you can chip in and let us know to which presenter that question was, just for clarification. If not, I'll move to the next question then. So from Olivier as well, to Hanae, what has changed so much in 1790 for Dijon? Can it be attributed to a specificity of this network, or is it a structural change?
As we saw for the evolution from the 1790 network to the 1883, it was basically an exploration process of evolution of the city. So there weren't really an impact on the accessibility of the existing network. And this is more related to the evolution, the process of evolution than the network properties. I hope I answered the question.
Because on two of your curves, it turns out the confidence bound. So it appears to be an outlier. And I was wondering if there was something very specific with this year and this network, of course, because each network, I think, comes from a different data source, or if it's really that the network was quite different at this time.
Yeah, so it was about the trajectory of evolution of the indicators, and yeah, indeed, it was somehow an outlier. And when we tried to explain this, it was more because in the 17th century network, it was really just within the city core and the fortification. And the 1719 was really the first process. So it was really a big structural change between the city within the fortification and then the network exploring outside those fortifications. So basically,
it's really a structural change from the closed city to a more open one.
Yeah, exactly. Yeah,
wow.
I thought it was about the other structural changes on accessibility, but when we are talking about the evolution of indicators, it's really a big structural change in the properties of the network from a really network within the fortification and extending outside them.
think we move to the next question. Oh, it's just Olivier, but if you need to chip in and clarify instead of reading it out, feel free, as definitely. Yeah, does the network only grow by the addition of new streets, or can you take into account suppression of streets and more drastic evolutions, such as what has happened during the Haussmann transformation in Paris?
Okay. Yeah, so thank you for the question. This is, I forgot to mention this, but the model is really to create organic evolution of the city. So considering, for example, what happened during the Haussmannian transforms, it's really a planned operation that changed really the whole structure of the city. But what we are trying here is really to see how this organic evolution and how to recreate it with the model, this organic morphogenesis. And for the part of addition of new streets and also suppression, we are trying to include the suppression of streets, but only when it's the most optimal option. For example, in one time step, a street is added, and then on the second one, we can find a part of the network that is optimal to connect it with another one. Then the model can suppress this road segment to optimize a new connection with the existing network. So, but the suppression is really small. We are really focusing just on the evolution and the organic one.
Okay, thank you for this. I think a last question to Hanae as well, from Antoine. Do you apply any weights on segments, or are they all treated the same? Avenues and versus food?
Yeah. So right now the weights, so our element on the analysis is not weighted, but this is a first step of this project, just taking into consideration the topological features and the shape of the network. I didn't talk about this in the research perspective, but also it's to connect the topology of the network with mobility modes. And here we can see the interest of applying weight on segments. For example, just a weight according to the topography of the city. And we can see with one way, it's gonna be more optimal for foot paths or for mobility, cycling mobility. And for another one, it's gonna be a more car-oriented. So the weighting the segment could be really a good next step to apply on this study.
Okay, thank you for that, Hanae. Yeah, we have another question actually to Michael. It's from Arthur.
Yeah.
How do you build this tree network from the vector field?
Yeah, basically the vector field is a displacement vector field. That means a vector, it represents the distance that can be make an element between the two different steps. And then I also created a set of moving elements that if you have a look at my papers, that they are typically always called the seed. Those elements that are moving elements that are moved by the vectors. So at each time step, I assign to this element a vector, and it moves in the following step. And the path that you have, it represents the edge of the networks. And that is the basic idea. Then also there are some other parameters, that probabilistic parameter that allow to increment or decrement this network. There are also some geometrical rules that ensure the planarity condition of these networks. That is the idea. You're welcome.
Okay, thank you for your clarification. I think we have 5 more minutes. If there are any questions, please feel free to chip them in the chat. And if not, I have maybe one last question to Arthur. You did mention, I think, that the focus and diffusion axis in your model becomes the motivation of residential settlement. So I was wondering, what are these motivations in a sense, whether they are based on any kind of economic decision-making theory or observed data that you have for any kind of cities that you observe or simulate in a sense.
Could you just repeat the end? I couldn't catch everything.
Yeah, definitely. So in your presentation, I think you had this sort of a clarification that the focus of the fusion axis is the motivation. It becomes the motivation of residential settlement, if I remember that correctly. So my question is really, what are the motivations that you take into consideration? Are they based on any kind of economic theory or observed or available observed data? And if so, is the model flexible with using different motivations in different situations, or is it sort of strict to specific motivations?
I think it depends on the actual city and actual neighborhood, what it looks like. For instance, it's more qualitative. We can assume that someone that is given the opportunity to go live in a beautiful residential area, if it's this type of neighborhood that he would go live in, he will be happy and his motivation to settle in would be high. And on the other hand, if a social housing building was built and some people are kind of forced to go live there, their motivation to settle there is quite low.
Thank you for this. I think we have 2 more questions.
Yeah, maybe I can add that it comes really from Richard, one of Richard's central idea of the political control of mobility. And actually, in some cities, you can observe pioneering behaviors. There are a few in a new neighborhood where there weren't any people like them, and this new kernel sometimes is really a core of a new neighborhood that will grow in time and so on. And so it's why we wanted to introduce this idea of motivation. So how do you how are you really engaged mentally in your new neighborhood, and also the convincing power of new behaviors that are witnessed in many cities.
Okay. Yeah, thank you for that. It was quite a clarification for me. We have 2 more questions. I think we have a general question that we will take last, I think, just to wrap up the session. And we have another question to Michael from Jiangye. He's curious if the software you developed can generate the city road networks retrospectively, like given the network of London, for instance, and how it looks now. Can it simulate what happened in the past?
Yeah, actually, a part of validation that I want to do is to compare the real data and also consider historical data. But the model, we have to be very careful with this kind of model, because in this, the approach that we use is completely decentralized. That is the focus. So we can make self-organized cities. It is not think it is not make it to constrain the network with the planned idea. So the model, it doesn't make, for example, regular grid, for example, something like that. So I know that London are a lot of part of London, and at least the middle age and the very old part is quite self-organized. So we don't have example like Paris with Haussmann and this kind of transformation. So that maybe in London it can be applied. Yeah. But clearly it cannot be explained all, because it doesn't consider, it's not a focus of this work. try to simulate the all kind of networks. We just focus on self-organized network.
Okay, thank you for this. I think we have another question that we can take, and then we will wrap up the session. So it's from Jengi as well to Bonin. I would like to know more details regarding the early stages of data preparation. You did mention the cell phone data, whether it's cooling data or not, and how the population flow between regions were generated.
Okay, for this question, I think this just to record the location of the signals and try to find out where they are located at the different zones, and trying to aggregate it into the 172 zones in the SDH area, and and trying to find out in what time it should be in the work, and that time should be their workplace, and maybe during the night time it should be the home place, and try to link the area between the workplace and the home place, and generating the population flow. Hope this helps you understand that.
Yeah, thank you for this. Yeah, I think we have a couple of more minutes for the last general question to just wrap up the session, and I will open this to all presenters. It comes from Olivier, where he mentions that in Turing's approach, as in Tom's, the morphogenes aren't actual chemical elements, but aggregated elements, more or less virtual, that are produced by actual chemical reactions at a micro level. Do you think that this meso level is a key element to morphogenesis? And I would leave the door open for any presenter to have this sort of general question. I mean, Olivier can definitely also chip in if he wants to make any clarifications. That would be great as well.
Yeah, maybe I wanted to have these questions because I'm always very surprised that we define easily the micro level. It's generally the individual level or the mechanism level. We also define correctly the macro level. For us, it would be, for instance, the city level or the megalopole level, but we are always a bit puzzled when introducing intermediary levels. And yet, it is really the key, I think, when you read the seminal paper by Turing, it is really the key to morphogenesis. It's that it's these A and B that Michele showed us with the equations are not actual, I don't know, proteins or reactants, or no, they're totally virtual. And Turing assumed that there is a very complex set of chemical reactions that can produce A at a rate X and destroy and so on. And so I was wondering, for our geographical applications, what are the good meso levels to consider? And it strikes me that the ways, for instance, that were presented by Hanae are such, to me, such an example of such a meso level. It's not an elementary element of the network, such as an edge, but it's really the key element to understanding correctly the network structure. So I was wondering if I was the only one to get to have this impression, or if you agree with me.
Yeah, Olivier, I think I agree with you, because I think that if you start from the complexity theories, that the first word that you see is that from from a lower level of interaction, we can obtain unexpected properties on a topper level. So, for example, for in my case, is the morphogenes that interact decentralized at in the lower level create a network that is at the top level. So is an emerging properties. The point is that that is one is that to find the how the distance between these levels. So it's a good idea that I have a problem also I have to think a lot about that, but it's an important perspectives and to good understand what is the feedback of the properties that you generated to the lower level. That is the point, I think. And another point that you can consider is not just one. So it's not possible to find just one level. We have to consider different.
Thank you for that, Chet. I'm also leaving the floor open to other presenters if they want to chip in. But if nobody has further comments on this, then I think we wrap the session with this. Thank you for attending this part of the session and for your interest in participating in the ECTQG. It has been really interesting with some really interesting discussions. I just need to sort of remind you that this session was recorded. So if any of the presenters at any point wants to stop or rather have us not share the recording on our YouTube channels, please do let us know. We will make sure it doesn't come up. And for the next session, the keynote lecture is at 5 p.m., which is around 45 minutes from now. So we hope to see you there, and thank you for the authors, definitely for the presentations, and thanks for the audience for participating with these very interesting discussions. Thank you, and see you soon at 5 p.m. UK time.